Hey folks, ever wondered what happens when you speed up, like really accelerate? You're probably thinking, nothing weird, just a bit of inertia to deal with, right? Well, hold on to your hats because in our fantastically strange quantum universe, speeding up might just flood you with warmth. I'm talking about a phenomenon so bizarre and elegant that it'll make you rethink reality, the Unruh effect. Let's dive in. Okay. So imagine you're floating far out in space. No stars, no planets, just you and the pitch-dark vacuum. Here's the kicker. The vacuum isn't actually empty. According to quantum field theory, it's a frenzy of particle pairs that pop into existence and annihilate each other so quickly you'd swear nothing existed at all. But here's where physics gets wild. If you're speeding up, if you're in an accelerating frame, the vacuum looks different. Warm, even. It's like the universe heated up just for you. This, my friends, is the Unruh effect. At its core, the Unruh effect says that acceleration creates a temperature, yeah, a literal temperature, in the vacuum around you. A stationary observer sees nothing but cold, empty space, but you, the accelerator, get hit by what looks like radiation. In numbers, the temperature, T, is proportional to the acceleration, A. Specifically, it's T equals h bar times A, all divided by 2 pik sub b, where h bar is Planck's constant divided by 2 pi, and k sub b is the Boltzmann constant. Sounds simple enough, right? But here's the thing, it's never been directly measured. Now you might ask, wait, how does that work? A warm vacuum? Is it real warmth, or just some optical illusion? Solid question. The effect arises because in quantum field theory, what you perceive depends on your motion. For someone who's stationary, space looks one way, but toss in acceleration, and the math flips on its head. What once appeared as nothingness becomes a field of particles with thermal properties. Technically, it's not the vacuum itself warming up, but your perceptual framework, your frame of reference, changing. An analogy? It's sort of like the Doppler effect, but for particles instead of sound waves. Alright, now, let's get into some history. This phenomenon is named after physicist William Unruh, who proposed it in 1976. Back then, folks were still wrapping their heads around quantum field theory. His theory was considered intriguing but largely theoretical. The equations hinted at it, but no one could really test the claim. Here's why. The temperature increase is, well, tiny, like really tiny. For noticeable Unruh radiation, you'd need ridiculous acceleration. Think near light speed spins around a star or something equally extreme. Most earthly experiments don't cut it. Our accelerations just aren't enough. However, theorists didn't give up. Over the decades, clever experiments have been designed using highly accelerated electrons, lasers, or even particle accelerators. Debate still rages over what counts as definitive proof, because the Unruh effect's temperature is so difficult to isolate from other noise. And what's even funkier? The Unruh effect ties into other weird phenomena like Hawking radiation. Yeah, that same radiation Stephen Hawking proposed for black holes. There's a deep mathematical connection suggesting that both these effects emerge from the interplay of relativity and quantum fields. Who knew vacuum particles could be so dramatic? Let's jump up a notch in complexity, graduate level if you're with me. The Unruh effect specifically arises when you switch from a Minkowski spacetime, the flat, four-dimensional stage of special relativity, to Rindler coordinates, which describe spacetime for an accelerating observer. In this transformation, the math predicts that what feels like empty space in Minkowski coordinates looks like a thermal soup in Rindler coordinates. Some researchers dig deeper into the implications. Could this effect hint at new physics, or even quantum gravity? After all, the Unruh temperature is related to fundamental constants like h bar and k sub b. Maybe it whispers secrets about the quantum structure of spacetime itself. Oh, and don't think this is all cut and dry. Alternative interpretations exist. Some physicists argue that the effect is inherently unobservable because you can't separate it from quantum fluctuations or other noise sources. Others suggest that the real magic is in our assumptions about space-time and what constitutes reality. Is the Unruh effect a limitation of our current theories, or an invitation to discover something even more profound? These are the headlines of modern debates in theoretical physics. All right, I know this gets heady, but it's also exhilarating, right? To summarize, the Unruh effect isn't just a theoretical oddity. It's a physical prediction showcasing how deeply linked quantum mechanics and relativity are. And it leaves us with questions as warm as the vacuum it describes. Could accelerating frames teach us new laws of nature? Could they unlock quantum gravity? If you're as intrigued as I am, hit subscribe, leave your thoughts in the comments, and help shape this channel's journey. Remember, we're brand new here, so every bit of feedback helps us grow. Stay cruised, stay hyper-focused, and remember, reality might just heat up when you least expect it.